So this is a recent work that I finished with Frank Hollander and Adrian Dolan. It's got a lot of open questions, and it's a beginning of an idea. So that's why I thought I'd present it. So the Moran model is a well-studied model in population genetics. It's powerful for many reasons. Primarily, as I'll state in the next few slides, the simplicity of it. It's very simple. It's the nature of it is in which all individuals exchange types each other. So it becomes a mean field model all at once and very tractable to study. Mathematically, in all these population genetic models, you require a dual that runs in reverse time. So your process is running forwards in time, and there's a picture backwards in time, and that's called the dual. And the Moran model has a very simple dual, which I will not go into. That's what makes it very handleable. And the model is simple enough that it can handle many biological aspects of genetic evolution, like mutation, selection, recombination, and migration, which I will not introduce today, but there's also one convenient coupling model to make it a very relevant model in population genetics. So the model is very simple. So I'll do a two-type model. So you can think of the two types will come in a second. It's part of the two alleles that I'll think of as two types. But broadly, what happens is I have a fixed population of n individuals. You can think of it as they having n genes, for example, and each individual will live an exponential amount of time, and then the individual is replaced. But what does replaced means? Replaced means that the individual chooses another one from the population to be its parent. So for example, and then each individual, you can think of it as carrying two types or two alleles, 0 or 1. So whoever you choose, you will imitate that person's type. So for example, let's just do a simple n equal to 3 structure. Let's say at time 0, I have one purple guy, which is 0, let's say, and I have two brown people at time 0. And let's say this is my individual X that I'm following, let's say. This is n equal to 3. So then let's say the clock ticks for n equal to 3. So for the other two people, the clock has not ticked, so they'll stay the same. And then at this time point, this person can choose this person's type, its own type, or its the other type as its type going forward. So the clock ticks, it dies, and it's replaced by somebody uniformly from the population. So for example, let's say the clock ticks for X at this point, and let's say it chooses this one. So once the clock ticks for X, your new state of the population is just this. So the number of purple alleles at this time was 1, now it's become 2, and that's how it fluctuates up and down. That's the model. So at each time your clock ticks, you look at the population and imitate somebody in the population. That's all we do. That's the simple Moran model. So what one models is the number of individuals, a certain allele, that is 0, and everybody else is 1. So that's what you understand. So you could think of it as a simple Markov chain. So you look at xn as the number of individuals, allele 0 at time t. So the number of alleles will go up by 1 at rate bi. What is bi exactly? You have I by n of your own people, and you should not choose anybody at n minus I. That's why it'll go to I plus 1. You'll go down by 1 if you take somebody from n minus I. It's something very simple. That's a simple Markov chain coupling with rates. So this is a very simple population genetic model, and once you have this, you can do many things. You can study classical things from Markov chain theory that tells you that you fixate. That means there's genetic diversity blows out in the population, everybody becomes 0, or everybody becomes a 1. This will eventually happen because you start zeros and ones, and every stage imitating its previous generation, you might lose out on ones altogether. You also compute the time to fixation. Here I put a p just sort of, not to confuse you, but p is just a proportion of allele 1. So some sort of, one can understand this a little better. This is n over p is like a, I'll show a scaling limit in a second, and this is like an entropy of the population. So it's a simple thing, you can do the model and you can do many more things. But what I'm interested is in large tail behavior. So here what I do is I scale time by n and look at the fraction of individuals of type 0. Okay, so this is just the fraction of 0 at time nt. That's what I'm looking at. So now this is a well-known theorem you can show in popular genetics, sort of made the model very tractable, is as yn goes, as if the initial fractions converge to a number y in 0, 1, then the process converges to what's called the right phase diffusion. So this, of course, I will not go into details how to explain this, but formally the idea is the following, that you look at the axis like this, 0 here, and this, let's say 1 here. So your diffusion, your y, will start at this point y. There's a Brownian noise coming from this w. So if you notice, it'll do something Brownian everywhere, here and there. And the moment it hits 1, that means this guy will kick in and it'll make it a 0, right? So the person will just stick to 0. That's how the process will evolve. That's like fixation of the genetic Moran model as well. Or you think of this person, what happens is like another possibility come down like this. When it hits here, this person becomes 0, so noise is 0, so thing stays constant after that. That's how the diffusion will move. So formally, that's what the right fish. But right fish is very easy to study. It's got good things. So you can understand the fraction of alleles at time nt in large times with regard to the right fish diffusion. And one of the ways of showing this is the following, is that you can write out a formal generator for the Markov process of yn, and you can do a simple Taylor expansion of this. You'll get it as the generator of the right phase diffusion plus a O of 1 n term. And this is the generator of y. This is one way of understanding how yns go to y. So what I wanted to discuss in this talk is, there's no reason why each of us have to have the same resampling rate. We may be genetically more fit or genetically a little less unfit. We may individually have different resampling rates. So I might resample at a faster rate than somebody else in the population, or vice versa, depending on my genetic fitness. So this is like a simple twist we're going to put in the model. And I haven't checked its application in terms of data, but something we thought about, that each individual, you assign a pre-chosen random rate of resampling. So that's rates are. So then can you understand this process? So you don't sample uniformly at rate 1, you have different rates for each person. Then it turns out that the model becomes quite non-trivial. Okay, let me just define it first. So here I would look at the number of people at time nt of type 0, but I also have to keep track of what rate they're resampling at. Before it was just 1, so I would just get xnt, but here I have to look at the entire resampling rate and the number of types of type 0. So the resampling rate doesn't depend on the type, it just depends on the individual. Then it turns out that the model becomes very, very non-trivial all of a sudden. We didn't expect it at all. So you need to impose some moment conditions on the resampling rate. So if your resampling rates are let's say R1's here, RK is here, and then it keeps on going, you need to know how the tail behaves and how these guys behave as well. So to sort of control it, I won't write these complicated conditions down. Then, of course, what it's expected that the process converges to a right phase diffusion, but with a different variance constant. Before d was equal to 1, here d is something that's like the inverse mean. So in some sense, if the resampling rates are very, very large or very, very small, it will affect this constant d. And if it's all 1, then it's the same thing. There's nothing. But you can't show like the usual way that the laws converge, because this Meyer-Zeng topology is what has to come in because of the following fact. That is, if you do a similar Taylor expansion for the whole guy, then what happens is that Thank you. What happens is that in the previous case, if you notice, this line was not there. You only had these two guys, and you had an O of n term, so the whole thing converged. But this generator is kind of blowing up in your face right here. So you can't do classical Markov process theory to show that the thing converges anymore. But what's cool about it is that this term vanishes if the process lives on the submanifold, where these coefficients are zero, where the nks are just a fraction of people with rks and so on and so forth. And y is the same as I by n. So what happens is that the process will contract to a manifold, but every now and then it will jump out of the manifold. So with exponentially small amount of time out of the manifold, but you quickly come back inside to the space. But when it does that, you can't show that the laws will converge. You can only show this Mayer-Zeng topology. Only certain functionals of the processes will converge. That's why this theorem is a little different and it's a little harder to show. The topology essentially involves that you will have functions of this form will converge, as opposed to the law converging. So again, mu k's are the probabilities with which you choose RK for the sampling distribution. So I'll just conclude with some open questions. The problem is intractable. We can't do uncountable support if the RKs, if the distribution R is uncountable. We can't do that. I think we can remove the tail and moment condition, a little bit of work, but we are not sure about this. I did only two-type model. You could do finitely many alleles. There's no problem. This is very hard to do, I think. This is very hard. These are very hard to do. Almost impossible. If you have infinitely many types, it's called Fleming-Vio, and it's very hard. I think, yeah. I'm done. Thank you. Yeah.
Hi. I have a question about the resampling rates that you were talking about. So what I understood originally, maybe this was wrong, was that in the original Moran model, you just sample, if you have two alleles, 0 and 1, you're just sampling an individual of type 0 or 1 with as much probability as their composition in the population. Now you want to change that. You want to bias it towards individuals of type 1 or 0.
No, I'm not. I'm just saying that the resampling rate of the individual changes.
Okay.
Not the way you choose the types. They remain the same. That's uniform. But it could be that I have some genetic defect that I resample quicker and quicker. So I might just induce someone who's having a 0 might stay long, will never resample and stay 0 forever. But I'll keep changing again and again. So I might fix it.
Okay, I see.
Just the clock of changing. I'm not changing the fitness landscape. That'll remain the same.
I see. Okay, so this is why you still get the D.
That's right. You get the same
DW.
Yeah, exactly. Right.
And it's not a biased walk.
That's right. There's no drift. There's no genetic drift.
Got it. Yeah. Got it.
It's just, you think of it as just a random imposition on the process itself.
I see, and that's why you're calling it random environment, basically.
That's right. Rather than I'm not introducing selection or fitness and.
Okay, I have many more questions, but I'll ask them to you later.
Other question? If you have any other question, you can ask.
It's an interesting model. I think these questions are, if you're anybody interested, even numerically to do these things, quite interesting to do, I think.
Maybe the only comment I'll make is that this is the model I've been teaching in class nowadays, and so I think both me and my students are very interested in these questions.
Happy doctor, yeah. Yeah, that's easy to see. I think that's like, for example, that just, you can just think of it as naively. If you, let's say you have a clock of rate 2, I have a clock of rate 1, then our net rate is 1 by 1 plus 1. That's naive. That's naive way of thinking immediately. Of course, the countable case is a little harder. The finite case is easier.
Maybe I can ask. In the start of the talk, you had this second point about being a dual model. Yeah. What is the dual picture? I'm not quite getting it.
Dual picture is the following picture. So let's say you, let's say I start with, let's say, 2 purple, purple, brown for the time being, let's say, right? Let's say the clock of the first guy ticks, and then the first guy imitates this person, let's say, okay? So then I bring down this guy here, this becomes a brown, this stays a pink, this stays a pink. And next guy becomes, let's say, another, at this time, this guy becomes a purple, let's say, from this person, let's say. So going forwards in time is this way. If you go backwards in time, it is just, all you're accounting for is how the death of this guy becoming a brown and this guy becoming a black. So it's like so this backwards in time process is the dual of the forwards in time process. You can write out the backwards in time a little differently. We track it. So we track this guy's type. It's, I'm not explaining this correctly, but this is broadly the idea is that if you look backwards in time, you have another process that matches the guy coming forwards in time. It's like a death process, essentially. So you have to look at a certain functional and it will come out from that. This is called Markov-Ross duality. I have write notation out to explain it correctly. I'm not doing it correctly.
Okay, so let's thank Siva.
Yeah,
Let's talk.
Thank you.